The timeline of recovery is rarely circular, but in the case of the Bell P-39Q Airacobra, the math was exact. On April 11, 2014, two divers descended into the cold suspension of Lake Huron. David and Drew Lozinski were conducting a search pattern about 4 miles north of Port Huron, scanning for metallic signatures on the lake floor. They were not tracking a vague legend. They were looking for a specific aluminum return. At a depth of about 30 feet, they located a debris field, and the state's maritime archaeology team logged the site for the record. Exactly 70 years to the day earlier, the aircraft struck the water and vanished. They were after one aircraft in particular, Second Lieutenant Frank Moody's fighter. Moody was an Army Air Forces pilot trained through the Tuskegee program, moving through a segregated training pipeline that included advanced gunnery work out of Selfridge Field. In 1944, Lieutenant Moody was executing a live fire gunnery exercise. The P-39 Airacobra was a unique machine, designed with an Allison engine mounted behind the pilot and a 37mm cannon firing through the propeller hub. The mission profile required operating the aircraft at the limit of its performance envelope while engaging targets. During the exercise, the aircraft suffered a catastrophic failure and struck the water. While Lieutenant Moody's body was later recovered near the St. Clair River area in 1944, the aircraft itself disappeared. The survival of the evidence for 7 decades is shaped by the specific hydrography of the site. This is the technical concept of freshwater preservation. Unlike the corrosive electrolyte solution of the ocean, the fresh water of the Great Lakes generally contains far fewer chlorides that accelerate galvanic corrosion. In a saltwater environment, aluminum structures and steel engine blocks can deteriorate rapidly over time. In the cold, low-oxygen water of Lake Huron, the chemical attack is often slower, and key components can retain recognizable geometry and surface detail for decades. That stability can give investigators a stronger forensic baseline for reading fracture surfaces and impact damage, even long after the crash. However, this preservation comes with a biological constraint. The static stability of the hard surfaces makes them an ideal anchor for invasive species. The wreckage discovered by the Lozinski brothers was not a clean aluminum skeleton. It was heavily encrusted with mussels. Thick layers of living growth obscured serial markings, data plates, and structural seams that would normally allow immediate identification. The divers had to look past that biological layer to recognize the distinct shape of the P-39 wing structure and the instrument panel. The condition of the airframe presented a second challenge for the survey team. The aircraft did not ditch intact. The violence of the collision with the water produced extreme hydrodynamic loads and rapid deceleration, driving the airframe into a state of disarticulation. The kinetic energy of the impact overcame the structural rivets, shredding the fuselage and separating the major components. The debris field is not a single point, it is a scatter pattern that extends for almost half a mile. The tail section was severed, the wings were torn loose. The heavy engine block was ejected from its mounts. This distribution confirmed that the aircraft hit the water with massive forward velocity, ruling out a controlled ditching attempt. The discovery on the 70th anniversary closed the loop on the location of the crash, but it opened a new technical file. The wreckage was now a known variable. The state of Michigan and the National Oceanic and Atmospheric Administration recognized the site not just as a memorial site, but as a forensic scene. The location was verified. The identity of the pilot was confirmed by the historical record. But the cause of the accident remained buried in the silt and mussel shells. The search was over. The work became documentation, verify the location, photograph the metal, and build a record that could survive scrutiny. The answers were hidden in the scattered metal, but only if the team could read the evidence without destroying it. And one likely suspect sat right in the aircraft's nose. The primary weapon system of the Bell P-39 Airacobra relies on synchronization with zero margin for error. The aircraft carries two .50 caliber machine guns mounted in the nose cowling. These weapons are positioned directly behind the arc of the 3-bladed propeller. To fire forward without destroying the aircraft, the guns depend on a synchronization system timed to the propeller's rotation. Its job is simple and unforgiving. Prevent a round from leaving the muzzle during the split second a blade crosses the line of fire. If that timing slips, the system fails. In Lieutenant Moody's case, the surviving damage pattern and historical reporting point to a moment when the timing didn't hold. When the pilot engaged the trigger, even a brief slip could send rounds into the propeller arc. At 2,000 revolutions per minute, one strike was enough to trigger a catastrophic sequence. The physics of the loss are defined by the concept of the propeller strike. When the bullet struck the blade, it compromised the structural integrity and the aerodynamic profile of the component. At high rotational speeds, even a small loss of mass or a slight deformation creates a violent imbalance. The propeller assembly is precision balanced to rotate smoothly. The bullet strike destroyed this equilibrium. The resulting vibration would have been immediate and severe enough to threaten the engine mounts. The pilot likely experienced a complete loss of thrust and an uncontrollable shaking of the airframe. The aircraft stalled and entered a descent that the pilot could not arrest. Verification of this sequence required physical proof. During the investigation of the site, divers located the propeller assembly. It had been sheared from the engine, a testament to the violent forces at impact. All 3 blades were recovered. Freshwater had kept the metal legible enough for close inspection. On one of the blades, investigators reported visible punctures consistent with ballistic damage, distinct from tearing caused by impact with the bottom. This discovery transformed the site from a general wreck into a documented accident scene. The propeller damage became a hard anchor, physical, legible, and consistent with a self-inflicted mechanical failure rather than enemy action. But the full debris field still mattered, because every recovered piece could sharpen what happened in the final seconds. The blade marks didn't just suggest a story, they fit the aircraft's geometry like a key. The condition of this evidence also highlights the selective nature of the environment. While the freshwater environment retarded the chemical corrosion of the aluminum, it did not protect the site from the kinetic energy of the crash. The vibration and the final impact scattered the wreckage, creating a chaotic field of debris. The engine was torn from the fuselage, the wings were separated, the cockpit section disintegrated. This fragmentation means that the story of the crash is not contained in a single hull. It is distributed across the lake bed. The recovery team faced a critical decision based on this distribution. There was no single airframe to hoist, only a dispersed puzzle. The evidence of the interrupter gear failure was locked in the propeller, but other clues regarding the trim settings, throttle position, and instrument readings were buried under silt and a living crust. To understand the full scope of the accident, the team had to look beyond the smoking gun of the propeller and read the entire scatter pattern. The integrity of the investigation depended on correlating these separated pieces without disturbing their context on the bottom. The geometry of the crash site dictated the strategy of the investigation. Because the aircraft had suffered a high-speed structural failure, the wreckage was not a single coherent target. It was a long, linear scar across the lake floor. To understand the sequence of the breakup, the recovery team could not simply swim to the engine and attach a line. They had to treat the entire area as a crime scene where the location of every rivet carried specific forensic weight. If a diver moved a component before it was recorded, the context of that piece was lost forever. To solve this spatial problem, the state of Michigan and the National Oceanic and Atmospheric Administration moved to debris field mapping. This process replaces random searching with a disciplined grid system. The site is divided into square sectors, and each sector is systematically surveyed. The goal is not just to find objects, but to record their orientation and their relationship to one another. A piece of wing skin lying upside down 50 feet from the fuselage tells a different story than a piece lying right side up next to the tail. This mapping establishes the distribution pattern caused by the disarticulation of the airframe, allowing historians to reconstruct the final seconds of the flight based on where the pieces landed. Executing a survey of this magnitude at a depth of 30 feet required a specialized workforce. The operation drew on professional maritime archaeologists and trained volunteer divers, including teams associated with Diving with a Purpose and other black diving organizations that have supported Great Lakes heritage work. These were not recreational tourists collecting souvenirs, they were trained recorders operating under the supervision of the state maritime archaeologist. Their role was to document the site without disturbing the sediment. They acted as the sensor network for the project, swimming precise lane lines so the grid was covered end to end. The volunteers utilized the technical concept of photogrammetry to create a permanent record of the site. This method involves capturing thousands of high-resolution photographs of the wreckage from multiple angles. Computer software then analyzes the parallax between the overlapping images to generate a three-dimensional model of the debris. This digital twin allows researchers to measure the distortion of the metal and the trajectory of the debris without physically touching the artifacts. It freezes the site in time, preserving the exact layout of the wreck before any recovery operations disrupt the sediment. This rigorous documentation was critical for confirming the integrity of the site. The mapping revealed that while the aluminum was encrusted with mussels, the underlying debris field remained largely untouched since 1944. The survey located the instrument panel, the radio equipment, and the scattered ammunition. It confirmed that the site had not been looted by salvage hunters. The position of the heavy components, specifically the engine and the propeller assembly, provided the anchor points for the grid. The data gathered by the Diving with a Purpose team converted the scattered aluminum into a coherent archaeological map. They proved that the wreckage belonged to the specific P-39 flown by Lieutenant Moody. However, the survey also highlighted a limitation. A map can preserve the location of the evidence, but it cannot stop the chemical degradation of the material. The survey confirmed that the aircraft was stable in position, yet the metal was still subject to the slow attack of the aquatic environment. The documentation was complete. The team now faced the physical challenge of converting a digital model into a recovered artifact. The survey phase was over. The extraction phase had to begin. The transition from visual documentation to physical recovery introduces a new category of risk. While a camera can capture a debris field without disturbing the sediment, raising a 1,200-pound engine block requires the application of force. The structural integrity of the artifact is the primary operational constraint. After 70 years of immersion, the steel and aluminum components have settled into the lake bed. The mud creates a suction effect that increases the force required to break the object free. If the recovery team applies too much tension too quickly, the artifact can fracture or the rigging points can fail, causing the object to fall back to the bottom. To mitigate this risk, the recovery team employed the technical concept of the lift bag. Unlike a surface crane, which applies a rigid vertical vector that transfers wave motion directly to the load, a lift bag provides a dampened pneumatic solution. The device is a heavy-duty bladder attached to the artifact by divers. The team introduces air into the bag using a regulator. As the air volume increases, it displaces water, creating positive buoyancy directly at the source of the load. This method allows the divers to control the ascent rate with precision. By carefully venting the air as the bag rises, they can maintain a neutral buoyancy that allows the heavy engine to float gently off the bottom, minimizing the stress on the weakened metal. In August 2023, the project moved to the extraction phase. The target was the Allison V-1710 engine. This component was critical not only as a museum artifact but as a diagnostic anchor for the investigation. Working in limited visibility, divers carefully cleared enough sediment to secure lifting rigging to the block under archaeological oversight, minimizing stress on weakened metal and attached fittings. Once the engine was rigged and the lift bags were inflated, the component broke free from the lake floor. It was guided to the surface, where a crane on the recovery barge took over the load. The moment the engine breached the surface, the operation shifted from a salvage context to a legal context. This transition is governed by the technical concept of chain of custody. This protocol is the documented timeline of the evidence. It requires a continuous written record of every person who handles the artifact, every location where it is stored, and every procedure performed on it. The chain of custody ensures that the provenance of the item is unassailable. For the Tuskegee P-39, this meant that the engine was not just a piece of salvaged scrap. It was treated as U.S. government property recovered under permit and in coordination with the relevant authorities. The tag attached to the engine on the deck of the barge linked it directly to the survey maps generated by the Diving with a Purpose volunteers. It confirmed that this specific block came from the coordinates associated with Lieutenant Moody's aircraft. The successful recovery of the engine was a validation of the method. The lift bags handled the weight and the rigging held. The freshwater preservation of the lake had kept the engine largely intact, but the environment was about to change. As the water drained from the cylinder banks, the artifact was exposed to the atmosphere for the first time in 7 decades. The stable, low-oxygen environment of the lake bottom was replaced by the oxygen-rich air of the surface. The recovery was a success, but the physical threat to the metal was just beginning. The team had won the battle against gravity, but they were now in a race against chemistry. The limiting factor in marine salvage is rarely the lifting capacity of the crane. It is the storage capacity of the laboratory. Following the successful extraction of the engine and the propeller, the recovery team stood at a logistical crossroads. The remainder of the Bell P-39 Airacobra lay scattered across the lake floor at a depth of 30 feet. The wings, the tail section, and the fuselage panels were accessible. The diving team had the expertise to rig them, and the lift systems used for the engine were capable of raising lighter aluminum structures. But the work moved into a phased posture. Major lifts beyond the diagnostic components were deferred, leaving large sections in situ until conservation capacity could match the scale. This operational stop was dictated by the technical concept of conservation first. This protocol establishes a strict boundary for underwater archaeology. It states that an artifact must not be removed from a stable environment unless the resources exist to immediately stabilize it in the new environment. The recovery of a submerged aircraft is not a single event. It is the beginning of a long industrial commitment. Every square foot of aluminum raised from the lake requires a corresponding volume of tank space filled with conditioned water. If the recovery team lifts more metal than the laboratory can process, they are not saving history. They are actively destroying it. The operational constraint in this case was the physical footprint of the preservation infrastructure. The Tuskegee Airmen National Museum in the state of Michigan had secured the tanks and the chemistry required to treat the engine and the guns. These are dense, high-value components that fit within standard containment vessels. The wings of a P-39, however, present a massive surface area and a complex geometry. To treat them would require the construction of custom pools large enough to submerge the entire span. Without this infrastructure in place, the aluminum skins would begin to deteriorate the moment they dried out. The risk of rapid corrosion drives this trade-off. In the water, the aircraft had reached an equilibrium with the environment. The freshwater preservation effect had slowed the degradation to a near halt. If the team had raised the wings and placed them on a dock without immediate chemical immersion, the oxygen in the atmosphere would have attacked the unstable surfaces. The drying process causes the cellular structure of waterlogged materials to collapse and accelerates the oxidation of the metal. The decision to leave the airframe in the lake was not an admission of defeat. It was a calculated strategy to maintain the integrity of the evidence. This decision created a bifurcated site. The engine, the propeller, and the weapons were transferred to the conservation facility to undergo electrolysis. The rest of the aircraft remains in situ. This split outcome aligns with the dual nature of the site. It is both a forensic evidence field and a memorial to the 22-year-old pilot. By leaving the majority of the structure on the lake bed, the state maintains a physical sanctuary that respects the location of the loss. The site is monitored, mapped, and protected, but it is no longer targeted for total removal. The selection process prioritizes the narrative elements of the aircraft. The engine and the propeller tell the mechanical story of the failure. The guns tell the operational story of the mission. The wings and the fuselage, while visually impressive, do not add new data to the investigation of the crash. By recovering the diagnostic components and leaving the structural components, the project balanced the desire for a museum display with the hard limits of conservation funding and physics. The aircraft is now divided between the cold silence of Lake Huron and the controlled environment of the laboratory, a compromise that ensures the survival of the story without bankrupting the preservation effort. The final phase of the recovery does not take place in the water. It occurs in a controlled industrial environment where the priorities shift from lifting weight to stabilizing chemistry. When the Allison engine and the propeller assembly arrived at the conservation facility, the evidence was intact but vulnerable. The mud and the mussels of Lake Huron had created a protective seal for 70 years. Breaking that seal exposed the metal to the atmosphere, initiating an immediate oxidation risk. To prevent the artifacts from disintegrating into rust, the team engaged the technical concept of electrolysis. This process is a primary method for stabilizing ferrous metals recovered from submerged environments. The engine block is placed into a controlled conservation bath and treated with electrochemical stabilization under professional supervision. Over time, the treatment helps loosen corrosion products and biological concretions, while reducing soluble salts and contaminants that can drive continued deterioration after recovery. For the P-39 project, this was not a quick wash. The process is a slow, methodical extraction of corrosion that can take months or even years depending on the density of the object. The conservation team had to monitor the voltage and the chemical composition of the bath daily. The goal was not to restore the engine to running condition. That is a mechanical impossibility. The objective was to stabilize the iron so that it could stand in dry air without crumbling. The treatment arrests the decay, freezing the component in its current state of damage. As the layers of corrosion were stripped away in the tank, the forensic narrative became clearer. The cleaning process revealed the serial numbers and the manufacturing stamps on the block, closing the final link in the chain of custody. These markings provided the absolute verification that this machinery belonged to the specific airframe assigned to Second Lieutenant Frank Moody. The conservation process transformed the object from a generic piece of wreckage into a personalized historical document. The culmination of this effort is the display at the Tuskegee Airmen National Historical Museum in Detroit. Here, the evidence is presented without reconstruction. The propeller blades are mounted to show the bullet strikes. The engine is displayed with its fracture points visible. This presentation strategy adheres to the principle of evidence first. The artifacts are not repaired to look like new. They are presented as they were found, carrying the physical scars of the accident. This allows the public to read the story of the mechanical failure directly from the metal. The legacy of the project extends beyond the museum floor. By successfully surveying the site, identifying the pilot, and recovering the diagnostic components, the operation fulfilled a dual obligation. It satisfied the historical requirement to document the loss of the aircraft, and it honored the service of the pilot. The 70-year gap between the crash in 1944 and the discovery in 2014 was bridged by procedural discipline. The wreckage that remains on the bottom of Lake Huron is no longer an unknown hazard. It is a monitored site, protected by the state and respected as a war grave. The decision to leave the wings and fuselage in the dark water ensures that the site remains undisturbed while the engine and propeller stand in the light as proof of the event. The recovery of the Tuskegee P-39 demonstrated that with the right combination of survey technology, lifting physics, and chemical conservation, even a scattered and broken history can be reassembled.